Okay, now the binomial series is a useful result. You won't find it in your formula book, but if you've done enough practice, you may remember it. In the previous example, we actually derived this particular series result, which is the 1 plus x to the power p equals the sum from n equals 0 to infinity of p times p minus 1 times p minus 2 times p minus 3 times dot 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 all the way up to p minus n plus 1 x to the n over n factorial for the absolute value of x less than 1. So we're going to use this in another expansion when we're actually given a different value of x. We're given minus x squared, and we're given a value of p of minus a half. So use the Maclaurin series expansion of 1 plus x to the p, binomial series, to write down the Maclaurin series for 1 minus x to the power minus a half. Okay, so we're going to just use what we've used before. 1 plus x to the p equals, well, it's 1 plus px plus p minus 1 x squared over 2 factorial plus dot 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 plus p minus 1 and so on, all the way up to p minus n plus 1 x to the n over n factorial. So as I was just saying, we have, so if you just compare 1 plus x to the p with 1 minus x squared to the minus a half, basically the x is going to become minus x squared in a bracket, and p is going to become minus a half. Probably going to need some brackets for that as well. So 1 minus x to the power minus a half. Well, it's still going to have the 1, so it's 1. The plus px term is going to be minus a half times minus x squared. Plus minus a half times minus x squared, like that, just to the power 1. Plus, then you've got p times p minus 1, so that would be minus a half. Minus a half minus 1 is minus 3 over 2. Then we've got x squared, so it would be minus x squared squared, all over 2 factorial. Plus, I am going to write the next term. Minus a half, minus 3 over 2, minus 5 over 2, minus x squared cubed over 3 factorial. So that pattern continues, and it goes up to, well, the last term, we know it's p times p minus 1 times p minus 2, all the way up to p minus n plus 1. So p minus n plus 1, so p minus n plus 1, well, that's going to be, p we said was minus a half, minus n plus 1. So minus a half plus 1 is the same as 1 minus a half. So it's going to be a half minus n. Okay, so this is going to be plus minus a half, minus 3 over 2, and so on, all the way up to a half minus n. And then you've got a minus x squared to the power of n over n factorial. Okay, so we're going to have to do quite a lot of simplification and pull out anything we can in order to get a pattern. So now I need to try and define this, and you just think, well, what's the same and what's different in each bit? So basically this 1, I'm going to keep that kind of separate because the 1 is kind of on its own. Everything else, you've got some minuses being times together, and you've got these 2's on the bottom, and you've got minus x squared being raised to powers, and you've got factorial, and all this stuff. The 1, I'm just going to leave it out. So we're going to see this equals 1 plus, and then we're going to try and get a series. The sum of, we'll leave the start point and the end, well, we know the end point is going to be infinity. But we'll have a think about zeros and ones in a minute. So basically, in every single term, you have, well, you've got a minus 1 raised to some power. So you think this can be minus 1 times 1. This is minus 1 times 3. The next one's minus 1 times 5. So there's always a minus 1 to the power n. So from those bits, just those minus a half, minus 3 over 2 being times together, there's always a power of minus 1. So in the first term, remember, we ignore the 1, you've got minus 1 to the power 1 there. Here you've got minus 1 squared, that gives you the sign. The next one you've got minus 1 cubed. And it's evidently obvious now that n needs to start from 1. So you've got minus 1 to the power of n in everything, right? You've also got these powers of 2. So in the first one, you've just got over 2 to the power 1, or times 1 over 2 to the power 1. Here you've got, think of that minus a half times minus 3 over 2. Think of it as minus 1 times minus 1 times a half times 1 times 3. So that's going to be over 2 to the power n as well. Because in the first one, you've got over 2 to the power 1. Here you've got over 2 squared. The next one, over 2 cubed, right? And then you've obviously got an n factorial in all of them. That's not difficult. 1 factorial, 2 factorial, 3 factorial. So that's times n factorial. And then you've got the actual bits. So once you pull out the minus 1 to the power n and the dividing by 2 to the power of n, then you've got 1 times 3 times 5. So you've got 1 here. The first term you just got 1. The second term you've got 1 times 3. Then you've got 1 times 3 times 5. Then you've got 1 times 3 times 5 times 7, and so on. It's going to keep going, and this sequence is the odd numbers. So the bit that, remember, if you compare it to the series that we started with, the base series, your p minus 1 all the way up to p minus n plus 1. So once we've pulled out the signage and the over 2 that's common to every single term, we just have 1 times 3 times 5 times 7 times 9, and so on. So times 1 times 3 times 5 times 7 times ... and hopefully you know by now that's the odd numbers. If we start from n equals 1, that's 2n minus 1. And that's just the nth term of the odd numbers. So that's nearly done. It's just now this power of minus x squared to the n. So if I think about this minus x squared to the n, I'm going to try and decompose that, see if I can pull another sign out of it. So basically, we're going to say minus x squared to the power n. Well, I'm going to think about that as minus 1 times x squared to the power n, which I'm going to think of as minus 1 to the power n times x squared to the power n, which can be x to the 2n. Okay, so now we're going to have times minus 1 to the n, x to the power 2n. So it's not easy at all doing things like this, but you've just got to pull out everything that's common to each. You've obviously got powers of minus 1 being times together in not only in the minus a half, minus 3 over 2, minus 5 over 2 bit, but also in the minus x squared. And on every single one, every bit product's got an over 2, over 2, over 2. So we can pull that out as an over 2 to the n, or times by a half to the n, whatever. So now, if you look at these two minus 1 to the n terms, so if we look at that and that, well, that can simplify it really nicely. Well, that is minus 1 to the n times another minus 1 to the n, which is minus 1 to the n plus n, which is minus 1 to the 2n, which could be written as minus 1 squared to the n minus 1 squared is 1, so this is 1 to the power n, which just equals 1. So if we go back up here, both of these terms can be cancelled off as they multiply together just to give you a 1. So now we have 1 plus the sum from n equals 1 to infinity of 1 times 3 times 5 times dot 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 times 2n minus 1 x to the power 2n over 2 to the n times n factorial. Okay, now this is quite a tricky step, and again it's practice and experience to actually think of this on a whim in an exam when you've got no time. Very, very unlikely. So here's what you do. You take top and bottom and you multiply them by this. 2 times 4 times 6 times 8 times dot 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 all the way up to 2n over itself. 2 times 4 times 6 times 8 times dot 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 all the way up to 2n. And that's going to do quite a lot. If you think about it, well, on the top, basically, it fills in all the gaps. So the 2 can kind of go in here, and you've got like a 4 can go in here, and then you're going to have a 6 and so on. Even after 2n minus 1, you're going to go all the way up to 2n. So on the top, it's going to be 1 times 2 times 3 times 4 times 5 times 6 times all the way up to 2n minus 1 times 2n. So on the top, you're going to have a 2n factorial, right? And obviously the x to 2n is already there. Now on the bottom, that is interesting. So I'm going to have to think about this in another way. So this 2 times 4 times 6 times 8. So 2 times 4 times 6 times 8 times dot 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 times 2n. Well, it could be written as 2 times 1 times 2 times 2 times 2 times 3 times 2 times 4 times dot 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 all the way up to 2 times n. And if you think about that, this term is the 2 times 1, the 2 times 2. It's just exactly the same thing written in another way. And so what that is, you're going to have 1 times 2 times 3 times 4 times 5 times 6 all the way up to n. So that you've got an n factorial. But you've also got 2 times 2 times 2 times 2. All for every term, there's a 2 being timesing it. So that's going to be 2 to the power n. So on the bottom, you've got 2 to the n times 2 factorial. That's in addition to the 2 to the n times 2 factorial that we already had. So you've got this that we already had, and it actually turns out that this is 2 to the n times 2 factorial anyway. So now our Maclaurin series is 1 plus the sum from n equals 1 to infinity of. Now, on the top, we just said we had 2n factorial times our x to the power 2n. On the bottom, well, you've got 2 to the n times n factorial, 2 to the n times n factorial times another 2 to the n times another n factorial. We can simplify this. If you think of 2 to the n times 2 to the n, well, that's 2 to the power 2n, which is 2 squared to the power n, equals 4 to the n. So I can have a 4 to the n, and n factorial times n factorial, we'll just write that as n factorial squared. So now a final expression for the series is 1 plus the sum from n equals 1 to infinity of 2n factorial times x to the power 2n over 4 to the n times n factorial squared. So if we go back up to the question, don't lose sight of that. So use the Maclaurin series to write down an expression. We've now done part A. So better label, that was part A. Part B, but we probably should say why it is valid, because we're certainly going to need to know why it's valid here. So remember, the initial binomial series is valid for the absolute value of x less than 1. So this is going to be the absolute value of minus x squared less than 1. So this is valid for the absolute value of minus x squared less than 1, which is exactly the same as before. The absolute value of x is less than 1. Okay, so I'm just showing you an extract from the formula book, the derivative of arc cos x. If f of x equals arc cos x, then f dashed x equals minus 1 over the square root of 1 minus x squared. So if I was to integrate minus 1 over the square root of 1 minus x squared with respect to x, well, that's going to get me back to arc cos x. So what we have is minus 1 over the square root of 1 minus t squared dt. So that's exactly the same, but with a t. And once we put the x and the 0 in, we're going to get back to the same place, right? And also, if we just think about what this is, so minus 1 over the square root of 1 minus x squared. And if you look at the expression that we've been finding in the Maclaurin series form, the only thing that's different between this and this is a minus sign is missing. So 1 minus x squared to the power minus a half. Well, power of a half means a square root. Power of a minus a half means the reciprocal, the square root of the reciprocal. So this is going to be 1 over the square root of 1 minus x squared. So then the only difference is that there's a minus sign missing. So if we were to integrate, we would have arc cos x minus arc cos 0 equals, or the integral of the negative of our series. We are going to need to know arc cos 0, because in a lot of cases when we've done similar things, it's been 0. Arc cos 0, basically for what angle is cos of the angle 0. So if we just draw a circle, cos of pi by 2. Cos of pi by 2 equals 0. So that means arc cos 0 equals pi by 2. So now arc cos x minus arc cos 0 equals minus 1 times the integral, remember, because we're missing that minus sign, between 0 and x of our series for 1 minus x squared to the power minus a half, but with t's instead of x's, and it's dt. So it's going to be all of this, but we need t's. So let's just put that there so we can see it. So minus the integral of our series, because remember, this is 1 over the square root of 1 minus x squared. That's a power series representation. 1 plus the sum from n equals 1 to infinity of 2n factorial. X to the power 2n will become t to the power 2n. And on the bottom, you've got your 4 to the n, which just stays. And then you've got an n factorial squared, which just stays. This is with respect to t. So now, just to give myself room, on this left-hand side, it is arc cos x minus arc cos 0, or arc cos x minus pi by 2. Okay, so arc cos x minus pi by 2 equals, so minus the integrand function. So if we integrate this with respect to t, well, the 1 is going to just become t. So the integral of 1 dt is just t, plus the series from n equals 1 to infinity, I'm just going to pull everything out that isn't related to t. So that would be 2n factorial over 4 to the n times n factorial squared. And then you've got times, well, it's going to be t to the 2n plus 1 over 2n plus 1. So remember, when you're integrating a polynomial, you just add 1 to the power and divide by the new power. That needs to be evaluated at x and 0. So that means arc cos x minus pi by 2 equals, now we can put everything in. And think about the 0, this is going to be 0 here, and this is going to be, the second term is going to be the 2n factorial over 4 to the n times n factorial squared, but then if t is 0, all of those terms are going to be 0, so that's quite helpful. So now I'm going to do two things. Firstly, I'm going to put the x in where the t is, that shouldn't be too difficult. Secondly, just think of what we've actually been asked to do. We've been asked to find a Maclaurin series for arc cos x. We do need to state which values of x is valid, but that's just going to be for x, absolute value of x is less than 1. So if we look at this, we know that arc cos x minus pi by 2 equals all of this. So arc cos x must be all of that plus pi by 2. So arc cos x equals, well, it's pi by 2 minus, remember we're now evaluating this antiderivative at x and 0, so t is just going to become x. There's another minus sign because we've got a minus sign outside of the bracket, so it's going to be minus this whole series from n equals 1 to infinity. So it's just going to be 2n factorial over 4 to the n times n factorial squared times 2n plus 1. So all of that times t to the 2n plus 1 is going to be x to the 2n plus 1. Okay, so this is a Maclaurin series for arc cos x. We know it's valid for when the absolute value of x is less than 1. But we do need to think about this in the context of arc cos x. So basically the domain of arc cos x is x between minus 1 and 1. We know that because if you think about arc cos, it's the inverse function of cos x. Cos x has a range between 1 and minus 1, so then the domain of the arc cos, the inverse function, goes from 1 to minus 1. So that's fine. Obviously, in the context of the series, we can't include the minus 1 and the 1. So this series is valid for x between 1 and minus 1, but it can't include them. Okay, we can move on to part C. So use the series in B, which was a series for arc cos x, to find the first three non-zero terms of arc cos x squared. And then part 2, hence find an approximation for the integral between 0 and 0.4 of arc cos x squared with respect to x. So we're going to use the series that we get, or the first three non-zero terms, in part C1, and we're going to integrate that in part C2. Okay, so just put this here for easy reading. So we know that arc cos x equals pi by 2 minus x minus the sum from n equals 1 to infinity of all of these complicated terms. We only need the first three terms. So if I just write out the first three non-zero terms of arc cos x, actually the first three terms are all non-zero. So this is part C1. Arc cos x, if it's only the first three terms, I'll say it's approximately equal to, well, the first term is just this pi by 2, that's the constant. So it's pi by 2. The second term is the x term, so that's minus x. And then the third term is going to be the first sum of the series evaluated at n equals 1, because it starts at 1. So you're going to have 2n factorial, so that's 2 factorial, or minus, because of the minus sign. You've got 2 times 1 factorial, so 2 factorial, which is just 2, times x to the power 2n plus 1, so x to the power 2 times 1 plus 1 is x to the power 2 plus 1, which is x cubed, over, you've got 4 to the power n, so 4 to the power 1 is just 1, times n factorial squared, well 1 factorial is 1, 1 squared is also 1, so that's just times 1, times 2n plus 1, well that's the same as the 2n plus 1 on the power, so that must be 3. Okay, so that means arc cos x, the first 3 non-zero terms is going to be pi by 2 minus x minus, or 2 factorial over 4 is 2 over 4, which is 1 over 2, and then you've got the other 3, so this must be x cubed over 6. Okay, they are the first 3 non-zero terms of arc cos x, but if we want the first 3 non-zero terms of arc cos x squared, then we need to just, wherever we see an x, we need to write brackets x squared. So arc cos x squared is going to be pi by 2. Well, we don't really need a bracket for the next one, so it's minus x squared. And then we've got minus x squared cubed over 6. So that is going to be approximately equal to, so arc cos x squared is approximately equal because it's only the first 3 non-zero terms. So it's pi by 2 minus x squared minus, for simple index law, x to the 6 over 6. And this is only valid for x, so the absolute value of x less than 1. Okay, part C2, hence find and approximate the value for the integral between 0 and 0.4 of arc cos x squared dx. So as I said already, we're just going to integrate this. So this is part C2. So the integral from 0 to 0.4 of arc cos x squared is going to be approximately equal to the integral between 0 and 0.4 of pi by 2 minus x squared minus x to the 6 over 6 dx, which is a very simple integral. So that is going to be, now we need the antiderivative, so we just integrate with respect to x, so it's going to be pi x over 2 minus x cubed over 3 minus what it's going to be x to the 7 over 7 times 6, so that would be x to the 7 over 42. And that needs to be evaluated at 0.4 and 0, which again is very friendly because when we put 0 in, it's just going to produce a 0. So now this is just going to be pi times 0.4 over 2, or even pi times 0.2, minus 0.4 cubed over 3 minus 0.4 to the 7 over 42. And just looking at what's going on here, it's probably not going to be a bad approximation, because think of 0.4 to the power 7, it's not going to be very big. And the next power of x is going to be bigger still, so that's going to make that term even really smaller. So we go to our calculators. Pi times 0.4 over 2 minus 0.4 cubed over 3 minus 0.4 to the power 7 over 42. And that gives us an answer of 0.606946 606,946. So we'll say that's approximately equal to 0.607.